Thank you very much, and thank you very much, Mike. I'm hoping everyone can hear me well. I don't think I was snatched back. I'd say, who wouldn't want to come back to this lovely weather in New York? I came back with open arms, although, as Mike said, I was here for many years, pre-COVID as a postdoc, so I'm very happy to be back at Columbia and Nevis and Science on Saturday. So I'm going to be talking about neutrinos, our friendly portal to the dark sector. Now, some of these words you may have heard, like neutrino. You may have heard of portals. You may have heard of the dark sector. The word friendly is here just because I think portals to the dark sector is a bit too mysterious for a title. But we'll see if you agree with me. So, neutrinos. Let's start at the top. What are neutrinos? So neutrinos are fundamental subatomic particles. Fundamental particles are the building blocks of our universe. And my job as a particle physicist is to take these fundamental particles, learn how they work, and put them together. Now, the best theory we currently have is called the Standard Model of Particle Physics. Now, it's written in a language called quantum field theory, which is a really interesting language to put on T-shirts and bedspreads, but it's not particularly interesting for talks. So I'm not going to be doing very much maths in this talk at all. So what is the Standard Model without this nice language? Well, it's basically a set of two things. It is a list of particles, so what matter is actually made from, what things are made from, and a set of instructions of how you put these things together. So interactions between those particles. And the idea is if you know these two things well enough, you can build anything you want. You can build atoms, you can build a universe, you can build anything. So that's the goal. So let's start. Let's build up the Standard Model. What makes up matter? Now, for a long time, people thought atoms were fundamental. Now, we now know that's not the case. Atoms are not fundamental. But everything you can see is made of atoms. So if you can make an atom, you can make everything else. So let's first make an atom. And to start, we'll need an electron. Now, an electron is a simple, very light, electromagnetically charged particle. It's what makes up electricity. So we need those. They orbit the atom. When you look at the protons and neutrons inside the atom, they are not fundamental. We thought they were for quite some time as well, but they are not. If you zoom in enough, you can see they're made from smaller particles. These smaller particles we call quarks. So you have an up quark and a down quark, and actually the proton and the neutron are just different combinations of these up and down quarks. So we can build protons and neutrons from these quarks. A brief aside, is it quark or quark? So Murray Gell-Mann, who picked the name, says it's quark. However, he chose the word from James Joyce's book Finnegan's Wake. So as both an Irishman, an Irish physicist, and a man called Mark, quark has to rhyme with Mark. And Mark in Irish is pronounced Mark, not Mark. So it's quark. Enough said. So we have quarks, and we can use these to build up the atom. Now, alongside the particle, we need some interactions, because if we just have some quarks and electrons, they'll fly off. So we need some way to attach the electrons to attract them to protons, and we need some way to bind the quarks together up. And it turns out we need two different things for this. We need electromagnetism. So this is a force that's carried by the photon of light, and this attracts the electrons to the protons. And we also need this strong nuclear force. So this is the gluon is the particle that carries this, and this is what binds all the quarks together. So with just these 5 things, you can build an atom. And you might think, great, this was easy. We'll be gone by 7:45. But I'm here to talk about neutrinos, and I haven't mentioned those yet. Where do they fit into the puzzle? I can build atoms with all of these. Why do I need neutrinos? And actually, it gets a little confusing when I kind of dig into it, because photons, electromagnetism, interacts with charged particles, and neutrinos are neutral. So they don't see photons at all. They don't interact with light at all. Now, just as quarks are called quarks, these two are called leptons. I'm going to use that phrase a few times, even though I try not to. My brain just says it. So if I say charged leptons, I mean these electrons. If I say neutral leptons, I kind of mean these neutrinos. But this doesn't have a fun word play associated with it. But neutrinos are neutral. They don't interact with the electromagnetic force. And gluons only interact with quarks. So I've just introduced a particle that doesn't interact with anything, and we can never see. That's very boring. And that's because this isn't the full picture. There is another force, which I kind of have glossed over, called the weak nuclear force. Now, the reason we kind of glossed over this is that it's confusing to explain. It doesn't, we can say this binds atoms together. We can say this is all of electricity and magnetism. This is kind of hard to explain. It turns out it governs a lot of nuclear decays, but they are not something you come across in your day-to-day lives. So it's kind of hard for us to talk about this. But it turns out that the weak nuclear force interacts with everything. Quarks, leptons, neutrinos, everything. It's kind of universal in that way. So we have a way to look at neutrinos through this weak nuclear force. In fact, the study of neutrinos is often called the study of weak interactions. Great. Now we finished it, you might say. Now we can wrap things up. The standard model is done. But it turns out there's 3 small kind of surprises that nature had in store for us. The first was there isn't just one set of quarks and leptons. There's actually a whole second set, and actually there's a whole third set. We don't know why there's 3 sets. We don't believe there's a 4 that we found, but 3 works really well. And these are kind of clones. So this entire row is cloned here, except they're a bit heavier. And we'll get to that later. But we actually have 3 sets of everything. So the muon and the tau are just heavier versions of the electron, and we also have associated neutrinos here. We also have a thing called the Higgs boson, which could be a lecture all in itself, and I imagine you have probably had lectures on the Higgs boson. I won't have a huge amount of time to get into that. I'll briefly touch on it. But this is what gives rise to the mass of all the particles. And also we have antimatter, which is doubling all the particles we have. So things get complicated kind of quickly. Now, for the most part, we're going to ignore antimatter in this, and we can just say this is what the standard model of particle physics looks like, and it works incredibly well. It can explain almost everything we see in the world today. Fantastic. So let's look a little bit more now that we have the whole picture as to how neutrinos slot into this. As I mentioned, electromagnetism works on charged particles, electrically charged particles. Neutrinos have no charge. Neutrinos do not interact with photons of light whatsoever. The Higgs boson gives mass to all particles. Neutrinos do not have mass, so it doesn't interact with those at all, and then Higgs only interacts with the massive particle. The gluon only interacts with the quarks, and the neutrino is not a quark. So the neutrinos only interact with a weak force. And turns out this is kind of interesting, because it's not that neutrinos only interact with this, it's that neutrinos are the only particle that only interact with this. Every other particle I've had interacted with multiple different forces, whereas neutrinos only interact with a weak force. And that gives them interesting effects. To see this, we kind of look at the scale of these forces. So the strong nuclear force, as you might imagine from the name, is the strongest. Electromagnetism is about 1% the strength of the strong force, which is still actually pretty strong. The weak force is much, much smaller, again. So if neutrinos only interact with this, whereas every other particle feels these forces, or multiple versions, you can see why neutrinos are extremely hard to interact with, and they're extremely hard to observe. There's other reasons as well, but this is really one of the key ones. So our job already as neutrino physicists is pretty hard. Now, there's a couple of times later in this talk, I'm going to say things like, we observe neutrinos, we saw a neutrino do this. I do want to be very clear, you can never see a neutrino. I will say the phrase, I've seen a neutrino, but I did not. Neutrinos do not interact with light. They do not interact with the electromagnetic force. So you can never see them in the traditional sense that I'm seeing all of you now. Instead, when I say we see a neutrino, I mean we have an experiment in which a neutrino hits off an atom using this weak nuclear force and kicks out something we can see. So here, for example, we smack the atom and we see an electron pop out. Now, electrons are charged. They interact with light. We can see those. So whenever I say that in the future, we see an electron or see a neutrino, you're going to think of this picture. Okay, so that's the standard model. I hope most of you are still with me. Next question is, I've just introduced this particle. It's very difficult to see. Where did they come from? So right here on Earth, most come from the sun. Most are coming from the sun. They're called solar neutrinos. Because nuclear fusion at the core of the sun, where you fuse together protons, knocks out a lot of stuff, but it knocks out a lot of neutrinos. Now this is taking place at the core of our sun, which here looks kind of small, but actually the core of the sun is about 18 Earths wide. And that entire region is basically constantly fusing over and over again. So as you can imagine, a lot of neutrinos come from the sun, a ludicrous amount of neutrinos. Now they go out in every direction, but some of them, of course, come to Earth. And if you're sitting here on Earth looking at the sun, you are basking in the glow of a lot of neutrinos. But neutrinos, as I mentioned, are very, very weakly interacting. If you're on the other side of the Earth, so it's nighttime, and you've got the whole Earth between you, those neutrinos don't care. They go straight through the entirety of the planet, out the other side, and through you still. They really do not interact very much. So if you're sitting here at nighttime, and all you can see is the Earth, if you look down into the ground, which we're almost getting to that point now, but not quite, if you look down into the ground and trace back to the sun, you can actually see the sun at night, looking down in the ground. you can see what the sun looks like through neutrinos. This is a photo of the sun taken at nighttime looking through the Earth. That's how much neutrinos just go straight through the planet. They really, really don't like interacting. And how many, you might ask? About 100 trillion solar neutrinos are passing through each of you every single second. And I don't mean just like once and then they're done. It's every single second. 100 trillion, 100 trillion, 100 trillion, and there's 100 people here. It's a lot of neutrinos. And that's constant, pretty much. But the sun is not the only nuclear reaction that's happening nearby. We also have things like nuclear reactors here on Earth, man-made ones. So this is a map of the planet, and I'm going to zoom in here to America. And you can see all these spots are the places where you can see a lot more neutrinos from reactors, which maybe, coincidental is exactly where we have nuclear reactors on the Earth. So we live here on the East Coast, and actually there's where most nuclear reactors in America, so we actually get something like 10 billion reactor neutrinos every single second passing through you. Again, constantly. Now this, of course, isn't as universal. If you went to Canada, there's a lot less nuclear reactors there, you wouldn't see as many. Go to Ireland, you'll have none. But there's still quite a few, 10 billion. We also have more natural sources. Atmospheric neutrinos occur when high-energy cosmic rays hit our atmosphere and create a cascade of nuclear decays. And we have lots of neutrinos coming from here. So about 1,000 atmospheric neutrinos are traveling through you every single second. And we can even go further afield, and we can look for cosmogenic neutrinos. So these are neutrinos that come from outside our galaxy. So huge dramatic effects like black hole collisions, or to be perfectly honest, we don't know where they come from. Very energetic neutrinos can travel for millions upon millions of years and get to us here at Earth. This, however, is very rare. You might have one cosmic neutrino passing through you every 10 million years. So slightly different to the 100 trillion that are passing through every second. So you might say, well, why do we care about atmospheric neutrinos or reactor neutrinos? We have 100 trillion solar neutrinos. Like, why are we talking about these rare events? And it turns out when it comes to neutrinos, it's not just how common. That's not the only thing we're interested in. So how many neutrinos passing through you per second is interesting. So we have very common and very rare events. We're also interested in how much energy the neutrino has. So neutrinos can go from very low energy to very, very high energy. Now, this is a log scale, so it's going over many orders of magnitude, many millions of times of events. But without getting into the details, if we look at where our neutrinos come from, these 100 trillion solar neutrinos I'm talking about are all very low energy. In fact, the lowest energy neutrinos we've ever detected were solar neutrinos. They're all up here, but there's a lot of them. Reactor neutrinos, again, now there's less of them, but they're higher energy again. They're living up here. And in atmospherics, the ones that there's only 1,000 every second, you might think, why do we care? It turns out they have a huge energy range, going up to very, very high energies. And that can be very interesting to study. Then right up here at the tail, we have these cosmogenic neutrinos. Extremely rare, but extremely high energy events. So this is why neutrino physics is interesting. We cover huge regions of energy, as well as very common and very rare events. Now, if you had asked me, if I was giving this talk this time last year, actually, and you had asked me, have we ever seen these cosmogenic neutrinos, I would say, no, we have never seen these, and there's a good chance they may not exist. But that changed, actually, last year. Or at least it probably changed last year. You can never be certain with these things, but a very fun experiment deep in the Mediterranean Ocean called KM3Net. So it's looking for neutrinos you go very deep into the Mediterranean where it's very dark, and you look for flashes of light from neutrinos. They claim to have detected what is the world's most energetic neutrino. And this may or may not work. So this is, here we are. So a neutrino's coming in, it hits off something and creates this charged particle, and this particle goes through the giant detector, which you can see is, the Eiffel Tower is not actually underwater, but this is the size of the Eiffel Tower relative to it. And you can see this massive amount of light flashing as this remnant of this neutrino goes by. And this is a single fundamental particle that's lighting up this huge, huge, vast part of the Mediterranean Ocean, which is pretty spectacular when you think about it. One single neutrino, which I haven't really told you much more than that they're very hard to interact, having this much energy. So 2.2 times 10 to the 17 electron volts. I haven't explained what an electron volt is yet, but from the sense of scale, this is the amount of energy it had, and this is the mass of an electron. This is how heavy an electron is. So very, very energetic. And actually, something very interesting happens here, because when we talk about subatomic particles, when we talk about energy, we're talking about these tiny things that you can't even see. So the energy scale is not relevant to us. I could tell you this is a huge number, but what does that mean to you and me? Turns out this neutrino had enough energy that you or me would feel, like it has enough, not that we would feel it if it hit us, it would go through us, but the energy it contained was a number a human could understand. Let's put it that way. So actually I have a demonstration. If anyone would like to feel what a neutrino would look like, please come and see me afterwards. But actually no, that's a bit of an exaggeration, because even though it is energetic, it's about as energetic as, I'll see if Mike's ready, it's about as energetic as a ping pong ball moving that fast, which is a little anticlimactic in some sense. There we are. But yeah, it's about as, that neutrino had the same energy of a ping pong ball or a table tennis ball moving at about 5 meters per second, so a really bad serve. So that doesn't sound very exciting, but then think about the details. This is one single particle. In a single table tennis ball, there is about 10 to the 23 particles. And yet somehow this had the same energy as this whole ping pong ball moving at 5 meters per second. So when I did that calculation, I was really hoping it was going to be some big baseball bat swing, but no, it's not quite. But it's still interesting. And it goes to show you the range that the range of physics and the range of energies that we probe in neutrino physics. It also helps that this is moving at a significant fraction of the speed of light. That's why it can happen. Okay. So the aim of that section was really just to try and convince you that neutrinos are everywhere, hundreds of trillions of them all the time. It turns out they're actually the most common particle of matter in the universe. And over the last decades, we have detected millions of neutrinos. We often say neutrinos are incredibly rare, and they are, but we have detected millions of them. We've gotten very good at this. We detected them from all these sources I mentioned here, but also there's lots of other sources that I don't have time to talk about today. But the crux of it is we study neutrinos from as many places as possible to get a better insight into the universe. And we've been doing this for a while. So what have we learned? What have we learned from neutrinos over the course of these millions of events that we're looking at, other than every so often we get a ping pong ball from space? Well, first off, we have learned that there are 3 flavors of neutrino. These are the 3 types of neutrino. We tend to use the word flavor in physics. We have the electron, the muon, and the tau neutrino. We also have these 3 flavors of the charged leptons, the electron, the muon, and the tau, as I mentioned. Now, when it comes to flavor, to tell these apart, it's quite easy for the charged leptons. It's just their mass. These particles are identical, except the muon is about 200 times heavier than the electron, and the tau is about an extra 20 times heavier than the muon itself. So we just see which one's heavier, and we can pretty much figure out which one's which. It's very easy. But if you remember, neutrinos are massless in the standard model. So how do we tell the flavor apart here? How do we even tell what the flavor of a neutrino is if they don't have mass? And that's actually kind of a tricky question. So from now on, I'm going to talk mainly about the muon and the electron, because they're the most common, and it'll just make the discussion easier. But let's talk about how we define flavor of a neutrino. We do what we all like to do. We do an experiment. So we have a beam. We have some amount of neutrinos we don't understand. We build a neutrino detector. Most of these neutrinos will pass straight through, as I mentioned, but every so often, one will hit. And what comes out is what's important. So an electron here pops out, so we can go, fantastic. That was an electron neutrino. Now, this might seem kind of obvious, but actually, this is how we define flavor. There's no other way to do it. We define the electron neutrino as the neutrino that, when it interacts, kicks out an electron. This is a strange situation where we're defining the type of a particle from a different particle, but that's the only thing we can do. And this actually is what we did to discover neutrino. We put a detector right beside a nuclear reactor, and when we ran it for a long time, we saw that we only ever saw electrons pop out. So we know that these were electron neutrinos or electron antineutrinos. In fact, this is how we discovered the neutrino back in 1956. And Rines and Cohen got a Nobel Prize for this with their project Poltergeist to look for these ghostly neutrinos. So then later on, when we started to look at other sources of neutrinos, this is the decay of unstable pions, for example, we did the same experiment, and you'd expect to see electrons again, but this time we saw muons. Just proving that the neutrino that hit here, coming from these decays, was a different neutrino to the electron neutrino. And this was also awarded a Nobel Prize. Leon Lederman, Melvin Schwartz, and Jack Steinberger, all of Columbia, got a Nobel Prize for this in 1962. So you can see why I chose to study neutrinos. It's clearly a good field. But this is how we prove there are, in fact, 2 different neutrinos. The same was done for the tau later on, basically the same premise. But this is where things started to get a little weird, because they repeated this experiment, effectively. So we take some neutrinos, we see they interact, only produce muons, so we can say, great, we have a source of neutrinos that's 100% muon neutrinos. But then we repeat the experiment a little further down. We move the detector down. And suddenly we see, oh, actually, no, maybe we're not right. We're actually seeing some electrons pop out. So some of the neutrinos must be electron neutrinos. And then we do it again. We move even further away. And suddenly, we're not really seeing any muon neutrinos. We're only seeing electron neutrinos. So you're starting to question whether your detector was just broken over here. And then you do it again. And you start to see, now you actually see muon neutrinos again. So something seems to be going very, very wrong with your detector, or something is going very wrong with reality. And if you were to do this more finely grained, you would find that the probability that you see a muon neutrino starts to change over distance. And the probability that instead you see an electron grows inversely. So, at the start you have a pure muon beam. As you go further and further, you get less muons and more electrons, and it starts to oscillate. And it really oscillates. It goes up and down. This would continue on ad infinitum if you could build enough detectors, if you get enough funding. And this is a real effect. This is not your detector breaking. This is a behavior that is unique to neutrinos, and it's called oscillation. And it's very strange. So it's very strange, and often it's hard to explain. So I have a couple of slides here to try and maybe get a bit closer. So, I almost lost my mic. I wonder if anyone's ever seen this toy before. It's the best way to describe neutrino oscillations I've ever found. So I have a muon neutrino in my hand. It's orange. And when I interact with it, I'm constantly interacting with it, and it's always a neutrino flavor. It just is a neutrino. I can jump it around, and it's orange. And that's the same with neutrinos. The only time you can ever detect them is when they interact. And at that point, they're always a fixed flavor, like this. But when they're moving through space, they don't actually move as a single neutrino. They move as what we call a quantum superposition of all flavors. So, for example, in this ball, what color is it? What color is it when it's moving? It's not really any color. You can't really see. It looks like this here if you can't see it in my hand. But then every so often, when you catch it, it's a different flavor. So it's a muon, throw it, and now it's green. And it's not that when it's traveling like this, it's traveling as one color. It is literally both colors, and then you catch it. You try and catch it, and it falls. These are great. If you want to play with these afterwards, come and let me know. But they give a really good idea. So they travel as this intermixture, and when you interact with them again, there's a chance it will be in a different flavor. See? Green and red. And that's what we see in neutrinos. We had it red. I threw it in the air. It is now both in some sense. And when you catch it again, or when it reinteracts over here, when the neutrino moves and reinteracts, there's a chance it reinteracts with a different component of it. But it's not a fixed thing. It's a probabilistic thing. This is analysis. Then analogy only goes so well. There's no weird quantum mechanics happening here. This is just a toy, but the effect is quite striking. And this is a real effect. This is something we've observed in many different sources of neutrinos around the world. But it's really weird. Now, not only is it weird, it's also really important. As it turns out, this was also another Nobel Prize for the discovery that neutrinos oscillate. Tajika-san and Art McDonald won this in 2015. But actually, it wasn't even that neutrino oscillations. That wasn't the reason they won it. Well, it was. But the second half of the sentence is more important, which shows that neutrinos have mass. And I've told you like 5 times neutrinos don't have mass, so I can see why you might be concerned about my authority right now. But turns out they might have mass. The reason this is a slightly complex connection, and it's my only equation in the talk, it turns out you can engineer this oscillation. This is something that you can easily have in the standard model, this oscillation behavior. It turns out this works only if this term appears. And this is oscillating sine squared. You have the distance neutrino gone, the energy neutrino has, and then the difference in mass of the 2 different neutrinos, effectively. So if the masses were 0, this whole thing would be 0, and this would never happen. Actually, you learn more. If the masses were equal, this would also be 0. So not only do we learn they have mass, we learn they have different mass, which is still interesting. So the simple fact that we see this oscillation proves they have mass. Now, this is a tiny, tiny mass. This wasn't something that we just missed for 20, 30 years. This is very, very small. We actually don't know the exact value. We know it's less than 0.5 electron volts. To give you an idea, that's 1,000,000 times lighter than the electron, the other lightest known particle we have, and it's about 1,000,000,000 times lighter than a proton. So I do not blame previous neutrino physicists for not figuring this out. It is very, very, very light. But it is not zero. And you might think, well, you know, a rounding error. Let's just call it zero. It's close enough. But actually, that doesn't work. Turns out, by the fact it's not zero, that breaks the entire standard model. This beautiful theory that we put together that works successfully in 99.9% of the cases, you cannot have neutrino masses in the current standard model. It completely breaks it apart. Everything's on fire. Which is concerning, because this is our best understanding of the universe at the moment. So this is perhaps, okay, I'm very biased, but this is the biggest puzzle we have in modern neutrino physics, is where neutrinos' mass comes from. In fact, you know, if we ranked them, I would put this as the biggest. I do rank them. This is the biggest puzzle in modern particle physics. This is probably the most interesting one. The only other one that might be as interesting might be something like dark matter. Have people heard of dark matter before? Yeah, so I'd say that's probably close. And wouldn't it be interesting if they were related in some way? So that's going to be the second half of my talk. And I'm going to remind people about dark matter before I jump in. So what is dark matter? Well, so dark matter became a question when we started looking into the universe. We started looking at galaxies. And galaxies spin. And when we look at galaxies, and we look how much they spin as you go away, so that as you go from the core, you can see how much they spin, we expect that they're fast spinning in the middle and they slow down as you go to the edge. That's kind of coming. If you look at all the stars and all the stuff we can see, that was what you'd expect the spinning to be. This is what we saw. It spins faster and a bit faster and then kind of flattens off, but it's very fast. So as you go to the edge, it's actually spinning faster than in the center. And this isn't just we saw this once and went home. We've seen this in pretty much every galaxy we have ever looked at. So that's a concern. It turns out you can explain this if, instead of just being the matter you see, if you have a large sphere of other matter, then the prediction matches basically. Instead of the galaxy being what you see here in this disk, it's this giant sphere of other matter, then things match up. But that's really silly, because we don't see anything there. So if this were true, this matter would have to be dark. So dark here just refers to doesn't interact with the standard model electromagnetism. It doesn't interact with light. So if whatever this is, it needs to be dark. Not only does it need to be dark, there needs to be a lot of it. If you look at the entire matter in the universe, everything that we know, all the atoms from the standard model, only are 15% based on what we can see from spinning galaxies and other things. 85% has to be dark matter. So not only it has to be dark, it has to be everywhere. Now the eagle-eyed amongst you might say, oh, a massive particle that has no electromagnetic charge. What about the neutrino? I've just told you they have mass. Could the neutrino be dark matter? No. That was clearly where this talk should have been going. It would have been great. And people did think this for a while, because neutrinos have mass. Neutrinos make up parts of the universe. Maybe they are dark matter. They do make up a tiny bit, but less than 1%. So it cannot account for this huge 85%. They're also too light. They move too fast. They wouldn't stick bound to the galaxies. They just go flying around. So neutrinos cannot explain dark matter. But the idea is sound. So if you came up with the idea in your head before I said it, good. The idea is sound. What if there's a different particle? Not neutrinos, but a different particle, which we're going to call dark matter. And what about this? This is also not electromagnetically charged. So maybe this could be dark matter. Saying this particle called dark matter could be dark matter is a little silly, tautological, but yeah, some new particle outside the standard model. And this is something that people have looked at for a long time. One idea is to say, well, neutrinos interact very weakly through the weak force. What if this dark matter particle also interacts through the weak force? We know it has to interact weakly because it can't interact through electromagnetism. We can't see it. So maybe it's like a neutrino interacts through the weak force. And that was a very well-studied idea. It still is a very well-studied idea. It's called a WIMP. You may have heard of it. A weakly interacting massive particle. I think they searched for it just because the acronym's great. But WIMPs are basically dark matter that interact only through the weak force. And we have a huge host of experiments around the world looking for this. Here at Columbia, people work on it. It could be, and probably has been, talks on dark matter research here before. But from point of view of this talk, all I will say is we have never observed anything that looks like a WIMP. And I'm not going to say we never will, but we've been searching for a while. It's not my personal opinion idea of what dark matter could be. But we do know dark matter exists, so we have to do something. So what if it's not the weak force? What if it's something else, something weaker than weak? Because we have never seen anything at the weak force level. So we have the strong nuclear force, we have electromagnetism, we have this weak nuclear force, and neutrinos interact here. What if we had something weaker than weak? And what's weaker than weak? Well, we're not the most imaginative. We called it feeble. The feebly interacting particles. So what if there's a new force, some dark force that is weaker than weak? It's a feebly interacting massive particle. We need to get better at that. But the idea is, let's say weak nuclear standard model is not quite small enough. Let's do something else. Let's couple some new particle even weaker, a feebly interacting particle. So you might think, okay, maybe, but where does this force come from? And to talk about that, I'm going to step one step back. So this is a good idea. I'm going to explore this more, but let's step one step back to the standard model. Because one thing I hope you've gained from this is that the standard model is pretty complex. We have 34 particles, 3 different forces. They form protons and neutrons. The protons and neutrons form atoms. The atoms form molecules. The molecules form biology, chemistry, and planets and stars. Like, there's a lot of physics going on. Practically everything you see here is just from the standard model. And yet this is only 15% of the universe's matter. The other 85% is one particle. That seems a bit, I don't know, strange. It seems a bit like standard model centrist. Why does 85% of the universe a simple particle of dark matter, whereas our 15% is incredibly complex? Now, you can invoke Occam's razor and say, simple is best. You don't need more stuff to explain everything we see. And that's true. But I still think it's a little strange that we have this much complexity in the standard model, which we know works very well, accounting for a small amount of the universe, and the rest of the universe people consider as just one thing. So the idea of the dark sector is to elevate dark matter, to bring it up to our level. Is to say, this is how complex the standard model is. I'm not saying the dark sector has to be that complicated, but let's allow it to be that complicated. Let's allow it to have multiple new particles. New dark matter particles, new other exotic particles. We can have new forces. Maybe they're similar to the standard model weak force. Maybe they're completely different. We can have rich complex behavior. We may even have dark protons or dark atoms even. Some people even say we could have dark stars, although that's maybe a little bit more out there. So why can't we do this? And well, the answer is you can, of course. And there is actually some motivation as well. Now, if these were two different, you could even imagine a complete clone of the standard model, one-for-one copy. But if they don't ever talk to each other, then it's kind of boring. They may not there. Like, one of the problems with dark matter searches is that dark matter may not even talk to our world. It might only be there gravitationally, but it would be very uninteresting. From a physics point of view, we want to explore more. So we look for a way to couple these together, and we call these things portals. Now, I was aware that when I titled this, Portals to the Dark Sector, everyone have in your mind what you think of when I say a portal to the dark sector. Is it like this? Is it, something like sci-fi, traveling through space? It might be, because portals to the dark sector, as much as it is a descriptive term of what we're doing, it's a little, I don't know, gimmicky of a name. So what I really mean here, the dark sector is not a place in space far away that we need to get to. It is simply another class of models that's separated from the standard model. And these portals are just ways of coupling a standard model particle to a dark sector particle. So maybe not as exciting as a sci-fi explanation. So it turns out, if you look at the standard model and the maths of the standard model that we build, there's actually only 4 ways to build these portals that doesn't break the standard model further if you consider neutrino masses. But there's only 4 ways you can do this in a consistent way. There's what we call the neutrino portal, there's a scalar portal, there's a vector portal, and there's an axion portal. Now, you might guess which one I'm going to be talking about. These are all very interesting, but I only really have time to talk about one, although the same level of interest could be applied to all of them. So let's talk a little bit more about the neutrino portal. What is that? So the neutrino portal starts off with neutrinos. So neutrinos are particles that exist in the standard model, and as I've mentioned, they communicate via the weak force. Let's now say, oh yeah, and they oscillate and they mix together. That's key. You have to remember that. Now let's introduce our dark sector, and let's put, say, dark matter in there. There could be other things, but let's just put dark matter for now. And this does not communicate with the standard model. It's not electromagnetically charged, it doesn't feel the weak force, it doesn't do anything. But let's also put in a new particle. I'm going to call it a dark neutrino, or a sterile neutrino. It has lots of different names. Really, it's just a particle similar to a neutrino, but does not interact with the weak force, or electromagnetism, or the strong nuclear force. It interacts with none of the standard model. It can interact with the dark sector. It can have its own forces. So at the moment, we're kind of just building up a different universe over here that's interesting, but so far they can't talk back and forth because neither of these particles can interact with the standard model. But it turns out, due to neutrino oscillations, this sterile neutrino, this dark neutrino, can oscillate with our current neutrinos. So despite the fact it doesn't interact with the standard model, it can still oscillate with our neutrinos. And this coupled, this kind of circle, is the neutrino portal. It's a way of connecting the standard model to the dark sector and potentially dark matter through physics that we know exists. We know neutrino oscillations exist. And it's not that far-fetched to think there could be another neutrino out there that oscillates as well. So this is what we call the neutrino portal. And it's really quite exciting. It allows us to take a neutrino experiment, one that we've worked on for years, one that we can study, and we can repurpose it. Instead of looking for neutrino interactions, we can now use it to probe the dark sector. We're still looking at neutrino interactions at some level, but the interpretation is very different. So it's a good recycling program for old experiments as well. Now, it means that all of these trillions of neutrinos that are passing through you right now might actually give us access to information about the dark sector as well. You also get something that's for free in some sense, tacked on at the end. It turns out, although this is not easy, the standard model has broken now that we have neutrino masses. The thing we need to fix it is a sterile neutrino. Turns out a sterile neutrino is a component that if you add, you can potentially help explain neutrino masses. Now, this is not easy, and it doesn't come for free, but it is the type of particle you need in order to kind of help us fix the standard model. And it basically, it is, it's a complex thing to actually search for and prove that this is happening, but it's certainly the neutrino portal is the thing that gives us the possibility to probe this. Okay, so I'm just going to wrap up with a couple of slides talking about how we're actually doing this and what our experiments look like to search for these. Because this isn't a hypothetical. We're working on these as we speak. So you might ask, well, okay, which of these many neutrino sources are you going to use to search for dark sector physics? All of them could, but I'm going to focus on accelerator neutrinos, one of the ones I didn't speak about earlier. So here, this work takes place mostly at Fermilab in Chicago, outside of Chicago, Illinois. And it takes place there rather than here at Nevis, mainly because we need a very large proton accelerator, which Fermilab has. So it accelerates protons to very close to the speed of light. And we take those protons, accelerated, and we smash them into a wall. Good brute force technique. This produces a massive amount of decaying particles. In fact, earlier on when I talked about the Nobel Prize from the discovery of the muon, from Lederman, Schwartz, and Steinberger, this was how they did it. They basically invented the neutrino beam. So we have a bunch of decaying particles, and they decay into neutrinos. So instead of things like reactors, which throw neutrinos out in every direction, or the sun, which throws them out in every direction, we've built a way of firing neutrinos in a very precise beam forward. So now if you were to come along and put some experiments, some detectors in here, you would be able to detect neutrinos very easily. And that's what we've done. So at Fermilab, we have what's called the Short Baseline Neutrino Program, which is a set of 3 large detectors placed at different intervals along this neutrino beam. They're all the same technology, and they're all active as we speak. Well, actually, so Micromoon ran for many years and has now actually shut down. SBND and Icarus are currently running. This is what SBND looks like before it was lowered down into cryostat, into the beam. But SBND is very, very, very close. This detector is very close to the neutrino source, where the neutrinos are coming from. So actually, this is going to observe about 1 million neutrino interactions per year. Now, I know I said you have 100 trillion passing through you per second, but that's just passing through you. This is where we actually measure them. In the totality of history, from 1956 to now, we've only measured about 15 to 20 million neutrinos, and this is going to measure 1 million extra a year. So it's an incredibly intense source of neutrinos. And what we get from these experiments is beautiful pictures like this, really. It gives us unparalleled insight into neutrino interactions. So what you're looking at here is a neutrino interaction. It is a subatomic particles propagating out. I've shown you loads of cartoons about neutrinos hitting things, and that's really what we see here. We have a neutrino coming in. Well, okay, this is a real event from data, so we don't know this is a neutrino, but it looks exactly like a neutrino would. We have a neutrino coming in, it hits an atom here, and it knocks out an electron, which looks like this. It showers. As it moves through space, it showers, and also knocks out a proton here. So we have this very clean image of these subatomic particles. And really, I love looking at these because it gives you, there's not many times you can look at subatomic particles and track their movement through space at this precision. We also have an example of a muon neutrino. Here we have a neutrino come in, hit here, knock out a small proton, and a very long muon. Muons travel very far distance, and then the muon decays to a little electron. So we can really start to track all the kind of minute details of how these interactions take place. And we're going to have millions of them. This is an example of loads of different topologies, different things that neutrinos can look like. It's really like a digital camera taking these photos many, many times a second. Now, luckily, we don't need someone to sit down and go through all these pictures one by one, although it is fun to do that. If you ever want to volunteer, you'll have many people be happy to. We usually use advanced machine learning image recognition algorithms to scan through these. But for the most part, they are very easy to digest from the human eye. Loads of different patterns. And our job then is to look through all of these neutrino interactions and to pick out the ones that look a little off, the ones that look a little different, the ones that could potentially give evidence of dark sector physics. And that's really where we are now. One of these pictures is not real data. One of these pictures is a dark sector particle. So I'm going to, on the next slide, I'll show you which one. So everyone in your mind, focus on what you think it is, and we'll see if you're right. It is this one. Hands up, anyone? Who knows? It just looks the same. It would be complete guesswork. That's the thing. It's very, very tricky. Because, as I mentioned, dark sector particles don't interact with our world in the way that we're used to. So what we see here isn't a dark neutrino. It's the result of a dark sector particle decaying further. So as a quick example, this is what this particle looks like. This is the case where a neutrino comes in and hits off an atom. But instead of then producing an electron, it produces a dark sector particle. It can, due to the fact that they mix and oscillate together, you can actually produce this instead, which travels a small distance. And then this, via some new dark force, decays back down into an electron and a positron pair. So this would be the type of thing we'd be looking for in a haystack of 1 million interactions. And if we saw something like this, could be Nobel Prize worthy. Well, probably not one event, but if we found a few of them, we could really start to prove that we're seeing some dark sector physics. And that's really where we are now. We're basically starting off this new searches for dark sector physics at short baseline mirror detectors. And hopefully in a year's time or 2 years' time, you can all come back and I'll stand up here and say, this is a real data event, we found it. So far, we have not. We've done some searches and we have not found it yet. Okay, I think that's about wrapping me up. Just to summarize, I hope I've convinced you all that neutrinos give us a huge amount of information, not just about neutrinos, but about the whole world. We can look inside the sun, we can look at faraway galaxies through these neutrinos. But the fact that they are unique, the fact that they can oscillate, gives them this new additional usage that I think really hasn't been highlighted as much in the past. Its ability to act as a portal to these dark sectors. And this is exactly what we're trying to do here. We're trying to utilize our current neutrino experiments and future neutrino experiments to really try and pin down some of these, and perhaps the biggest questions we currently have in not just neutrino physics, but in all particle physics. I think, yeah, that'll wrap me up. Thank you very much.